welcome to Digital Electronics. This is EET215. I'm Mr. Whitfield, your instructor. Digital electronics is the study of electronics that make computers and everything. So, we're going to talk about differences between analog versus digital, why using them, generating a digital signal, what a multivibrator is, defining logic levels, testing for digital signals, and using a logic probe and mounting ICs. Lots of fun stuff. All right. Analog versus digital. An analog signal is one whose output varies continuously in step with the input. We've all had AC at this point, so we know how that works. An analog signal is AC. Or it could also be DC. It's just that it varies with time. Okay, there's your analog signal. A digital signal is one whose output varies between two voltage levels. We call them high, low, 1 or 0. It could be 5 volts, it could be 0 volts, it could be 0 for the high and -5 for the low. Some older Volkswagens had a negative 12 volt ground, and 0 volts was your positive signal. All right. We're going to have these quizzes periodically through here. Just pay attention to them. Blah, blah, blah. And digital signal is one whose outputs decreases, boom, boom, boom. And analog signal, it varies in step. There we go. Why do we need to use digitals? Well, it's kind of hard to store an analog signal other than as a recording with lots of overhead. Digital signals can be this is on and off, so you can use transistors. We can use all sorts of things to determine on and off. Once you get past the on and off state, you realize the power of it, simply because you can use so much of it at a time. You know, all real world events are analog. Analog processing is simpler, it's faster. Old style, traditional electronics, I won't say old style, are generally analog. Think old tube radios, things like that. As opposed to today's internet radio or car radios that are used ICs. Let's get through these. I'm not going to read through this. Y'all can read through this as well as I can. If this was your only pass on it, I can understand it, but this isn't going to be your only pass on it. Now, when I switch from 0 to 5, I get this various states. You know, we call that generally bounce back or bounce. We try to avoid. You know, we debounce it so that once it hits the level, it stays at that level. A multivibrator, monostable, one shot, that once you trigger them, they generate a single pulse. Now, free running, astable, oscillates back and forth. And a latch, it goes high, stays there until it's told to go low again. It switches back and forth. Remember the phrase flip-flop. We'll be using that a lot in this course. That's also the name of our cat, flip-flop. Now here's a one-shot vibrator. Here's a free running multivibrator. Generally it can be a clock. We call it a clock, but it doesn't have to be a clock, depending on how it's configured and how it's designed, whether it does that or not. Here's another quiz. A lot of your quiz and some of your test answers come from these quizzes in the presentation, so pay attention to them. Logic devices interpret put voltages as high or low. TTL and CMOS families generally have a unique voltage profile. We'll get into that in a minute. And what TTL stands for transistor to transistor logic. CMOS stands for complementary metal oxide semiconductor. Notice the differences in where the high is versus this one. If this were a 5-volt signal, the TTL would see high as approximately 2 volts plus, whereas the CMOS has to see 4 volts plus to see it. Now these numbers here are a little more refined than the numbers I had earlier, but it does give you a little more context as to what I was referring to. We want to test for digital signal. We have multiple ways of doing it. LED output indicators, that's where we'll be doing a lot of things with the lab kits. When you deal with microprocessors, microcontrollers, you turn an LED on, things like back and forth. A logic probe is a specialized electronic device. We all use multimeters, oscilloscopes, and a logic analyzer is an advanced tool used primarily for digital circuits. Now, here's the transistor-driven LED output indicator. You turn the switch on. It turns on the transistor, which causes the current to flow through the transistor, lighting up the LED. Now with a logic probe, it's going to give you an indicator light. All that changes depending on the type of the probe. Some probes stretch the narrow pulses. If it gets too narrow, the probe could miss it. But when you deal with anything with higher frequencies, it's much better to use a frequency counter or a scope. Portion. This is really just showing you basically that would be no different than if we inserted this IC into a breadboard, like inserting a IC into a breadboard. Surface mount is really a challenge to work with.